Hi Ani.
Hi Janakiraman.
So in the last lecture we looked at almost the entire flow of taking an analog signal and converting it to a discrete time, discrete amplitude signal, right?
Yes.
And in the process we saw the concept of a sample and hold circuit. So I just wanted to pick your brain on what more we could do with the idea of a sample and hold. Essentially, if you have a switch and a capacitor,
Yes.
I just want to pick your brain on what else you could do, right? So you have a switch here, okay, and then you have a capacitor,
Okay.
C, okay, and let's say this is connected, right?
Yes.
The time varying signal, we viewed each time sample, discrete time sample, as a DC signal.
Yes.
Right. So let's assume that this is a signal, DC signal V volts.
Okay.
Okay. And now I'm going to close this switch, right? And we of course discussed that this has some finite small on resistance, and therefore you would have a transient current,
Yes.
I of t, and I of t goes to 0 as t tends to infinity, and the Vc of t as limit t tends to infinity will go to V.
Yes.
Okay. So now I want to make this problem a little more interesting. Okay. So I'll call this, maybe I'll redraw that circuit. I have a voltage here, V, okay, and a capacitor C1, okay, and then I have another switch, but this time it's going to another capacitor C2. Okay, so this is switch S1, S2.
I see. Okay.
Okay, so the timing of these two signals is important, right? So let's assume that this was controlled by phi 1, this is controlled by phi 2.
Okay.
So if we look at the time varying signal, the control of phi 1 and phi 2, let's say at t equal to 0, phi 1 goes high,
Right.
and then goes off. Okay, and we are assuming that it is time t1 it is on. T1 is large enough so that the capacitor C1 can completely charge. Okay, and then I have phi 2, which is also another control signal at T1, right, or sometime after T1 it goes high.
Okay.
So for another time, so okay, this is T2 and this is T3.
Okay.
So sometime after T1,
Okay.
it goes on between T2 and T3. Again, T3 minus T2 is large enough so that the capacitors can reach steady state.
Okay.
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 So what do you think will happen in this case?
Okay. So maybe I am going to start from t equal to 0.
Yeah.
And see what happens.
Yes.
Right. So I am looking at the first thing is to actually now the circuit will the network will look different in different different times.
Exactly.
So maybe during the first phase,
Yeah.
right, of where things look okay. So maybe from 0 to T1,
Yes.
I will draw the circuit.
Okay.
What
great.
it looks like.
So let's do that. Okay. For time 0 less than T1, what we see is only switch S1 is on,
Yes.
switch S2 is open, and therefore you're saying that the capacitor
C2 is completely disconnected from
is
existing.
disconnected from the circuit. So therefore the equivalent circuit is going to look like this, right? Okay, great. So this is C1,
And in fact,
we
in
can
this
even-
case,
yeah,
the switch
we
is
can-
closed, so we
It's
can even
a short circuit, right?
perfect. Yeah.
Great. So this is the equivalent circuit,
Yes.
and if I ask you the question Vc of t, limit t tends to infinity, the steady state value on the capacitor, assuming, that's why I said assuming T1 is large enough,
Yes.
right, this is going to go to
V.
V.
Yes.
Okay, great. So now on this side, just extending your argument, I'm going to look at what happens. So between, by the way, between T1 and T2,
Yes. So we actually have 4 phases.
Exactly.
So we have 0 to T1,
So let's
T1 to
do-
T2,
yes.
T2 to T3 and greater than T3.
Great. Okay.
Right?
So let's look at
Yes.
between T1 and T2.
Yes.
Right? When neither switch is on,
Both phi 1 and phi 2 are 0.
are 0, right?
Okay.
Yes, both switches are off. Effectively, what we have is you have this DC source here,
Yes.
V, okay. There is a capacitor C1, okay, which is also charged to V.
Yes.
Okay, I'll just putting that in brackets. And we are assuming C2 is, and we'll, can
You
we
don't know
also,
what it is? Shall we just say it is 0?
yes, so we will assume that VC2 of 0 minus equal to 0. That is at T equal to 0, this C2 capacitor was
Correct.
discharged.
Correct.
Right?
So 0 minus refers to the fact that it is just before T equal to 0.
Exactly. So we are looking at on this axis somewhere just here,
okay,
just to the left of 0. What is the value on these capacitors?
Okay.
And we are also saying C1
So in
also
fact,
is
yes.
VC1 of 0 minus is also equal to 0.
Yes.
Okay?
Okay.
Great. So, yeah. So this is nice. So essentially between T1 and T2,
So C2 is completely discharged.
yeah.
Its voltage is
So
0.
Is voltage is
C1 has V.
V.
And the voltage source is the voltage source.
Yeah, right?
Right?
Now, so therefore there are 3 independent disconnected circuits. They don't talk to each other.
Yes.
And assuming it's an ideal capacitor, ideal switch and all that, the voltage will stay
Yes.
forever. Great. So now let's look at the last phase. Okay.
T2 to T3. Yeah?
T2 to T3.
Okay.
Okay. So what we have here now is the switch S2 is closed, S1 is open.
Okay.
So what is your
So you now have C1 and C2 in parallel.
correct?
A network with the top plates of C1 and C2 connected.
Yeah. Right. So
Right,
let me
okay.
redraw that.
Okay. I see.
So this switch S2 is on. I'm not drawing the voltage source V because it's not part of this circuit.
Yes.
Okay. C1, C2.
Yes.
And if, and we can maybe write down that, right?
Yes.
VC1 of T equal to T2 minus.
Yes.
Check.
Okay.
Just before the switch S2 turned on, what is the value on the capacitor?
Yes.
We are going to say that is V.
Yes.
And this guy,
Was 0.
VC2 of T equal to T2 minus equals 0.
Okay.
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 So, there are a lot of interesting ways to look at this, right? So, so my first question is, can I treat C1 like a voltage source?
So I have a problem because I have learned how to use KCL, KVL to solve circuits.
Yeah.
But they normally say that there should be no charge accumulation at any nodes. It is very useful to solve, right? Now, in this case, so for example, if I apply KVL around this loop, it tells me that the voltage across the two capacitors has to be equal always.
Yes.
Right? I already have a problem because I am starting with a situation where one of them has a voltage, the other does not have any voltage. So the minute I connect them up, clearly KVL has to be satisfied, right? Say the circuit is going to behave such that KVL is satisfied. So I would expect that eventually after a long time, they should have the same voltage across them once you reach steady state.
Steady state,
right?
Right? Yeah.
That much I can tell.
Yeah.
Okay.
So let's take a step back. So what you are basically saying, right? Maybe I'll just redraw that here once more because I want to. Right? C2, C1.
Yes.
Initial voltage of V. So you're essentially first of all making a prediction that C2 cannot charge all the way to V. Right? Or what I'm asking is, can I replace this capacitor with a DC source like this? Okay.
Okay.
This is a DC
Now
source,
I understand.
right?
Okay.
DC
I don't think so. I don't
of
think so.
voltage V, right? Because if this were the case,
Yes.
and the T3 minus T2 is large enough,
Yes.
C2 should eventually just go to V.
See, I know that a battery can give any amount of current and hold the potential difference.
Yeah.
In other words, it has infinite number of charges. But the capacitor does not.
Exactly, right? So fundamentally, a battery that we saw, right, has almost infinite charge. In fact, if you remember the initial discussion when we discussed the mobile phone battery, we said 1500 milliamp hour.
Yes.
That itself indicates even a battery has finite charge actually.
That's right. That's right.
And you cannot supply infinite charge. So, of course, in this case,
this is an ideal voltage source.
Ideal voltage source.
Yes.
Okay. And therefore, this is infinite charge.
Yes.
Because it's an ideal voltage source. Okay. So, that itself sort of limits our idea here and is telling us that a capacitor has finite charge. So, how much charge is on this?
That's easy because I know that a capacitor charge is just the capacitance, the product of the capacitance and the voltage.
And the voltage. So, and this charge, is it changing over time?
It cannot, right? So, once you are charged, unless there is something else to supply charge, the capacitor does not produce charge of its own.
It cannot
Only a battery can, only a voltage source can.
Right. So, so let's see. So first of all, there is some initial voltage and this guy is initially 0.
Yes.
So, there is a potential difference straight away and therefore there is going to be some current, right? So, you will have some I of t.
Okay. So, what you are saying is C1 is going to charge C2.
Yes, C1 is going to charge C2.
But then it will lose some charge.
Exactly.
Right?
So, now again I ask the question, will the charge of C1 be same over time?
No, it cannot.
It cannot.
It clearly cannot.
So, I have
because it is losing some charge to C2. So, charge cannot stay the same.
So, when I say Q1, I have to talk about charge at a time.
At a time.
Which again is at T2 minus.
Yes.
Right? And this has to be C1 into V.
Now I understand. So what you're saying is the capacitance, of course, stays constant.
Yes.
But now if you're saying that if it's charging the other one, the voltage also cannot change.
Yes.
Voltage also cannot remain constant. It has to change.
Voltage also cannot remain same.
Makes a lot of sense.
Right?
Okay.
And so therefore you're going to have some current, right? So you were right in the sense that the KVL has to be followed, right? There's no any current that's coming out of C1 has to flow into C2 and thereby charge C2 up.
Yes.
Right? So so with that, let's just begin. So now, okay. So
and of course Q2 then is 0.
Q2 of T equal to T2 minus equal to 0
because we know it is discharged initially.
So the total charge in the system.
Okay.
Right?
Because there's nothing to give charge to these two capacitors from outside.
T equal to T2 minus is 0 plus C1V.
Yes.
Okay. So just a quick addition, modification. If C2 were to be initially charged to something else, then you just modify the initial charge.
Modify the initial charge.
Okay. Yeah. So we have so much of charge in the system, and now you have a current flowing. So let's just intuitively understand how long will this current flow.
So the current will flow till so the minute they have the same charge, current will no longer flow.
Yes.
Right?
Okay.
Or rather, the minute they have the same voltage, not the same charge.
Not the same charge.
Right?
Right? Exactly.
Yes.
The minute they have the same. So what is going to happen is you have I of t. So if you just look at, sample this at, let's say, t equal to t2 plus some small time instant delta.
Yes.
Okay. I will call this t prime. Okay. So if you look at this, you have had some charge being pumped out of C1 and that has to charge C2.
Yes.
Right, and therefore the charge in C2
Yes.
at t equal to t prime would have become C2 into some new voltage. The system would have now cannot remain at the same voltage because the charge is changing,
Sure.
right? And therefore it will come to a new voltage of t equal to t prime.
Yes.
Right.
Okay.
So if I look at the voltage here, V of t, okay, and as you said, these two are the same for both.
Yes.
Right. It has to change, right, and the same amount of charge has been lost
Yes.
by C1.
Okay.
Right?
Okay.
Now you can have a charge. I mean, you can have a current only if there is a potential difference.
Yes.
Right, and therefore eventually the current will stop. Right. I of t will be 0 when the voltage,
VC1.
yeah, Vc1 of t equals Vc2 of t,
Okay.
right, and therefore this, let's call this voltage as V final. Okay, both capacitors are eventually coming to the same
Voltage.
final voltage. Okay, so if you look at this, C1 and C2, the initial picture is C1 with an initial voltage of V, C2 initially discharged. The final picture is C1 final voltage of V final. C2 also has a,
Yes.
right. So now what fundamental concept can I use to sort of
So clearly the charge from C1 goes into C2.
Yeah.
So if I look at the total charge,
Yes.
even after it's reached V final,
Yeah.
that should be the same as the initial charge.
Because of conservation of charge.
Charge.
Right. So let me just also say this is final. Right. So basically we are using conservation of charge. This is a very fundamental law.
Okay. Because we can use it here because there are no other sources, voltage or current sources.
No other source that is able to pump in or take away charge.
Take away charge.
Right. And therefore the charge in the system has to remain constant.
Yes.
All through the process. Right. Okay. So therefore if we look at this, essentially this says charge remains constant. Okay. So which implies the initial of the system should be equal to the final charge of the system.
Agreed.
Okay. And here we know that Q initial, right, is just C1 times V,
Yes.
because C2 is 0,
Yes.
and the final here is C1 times V final
Yes.
plus C2 times V final.
Okay.
Okay, so this is
Yes.
what we have, right? And therefore we simply equate these two and we say C1 times V equals C1 plus C2 into V final.
V final. Okay. Oh, which means that V final. Oh. It just depends on the ratio of the capacitors.
Exactly. C1 by C1 plus
C2.
C2.
I see. Okay.
Okay, into V.
Okay.
Right?
So it's actually smaller because C1 by C1 plus C2 is lower. So because you have lost charge, the final voltage, the final charge on C1 is going to be smaller, the final voltage is going to be smaller automatically. Oh,
Exactly.
I see. Okay.
Right? So therefore, So the simplest case is if C1 equal to C2 equal to C.
Yes. It'll just be half the initial voltage.
Okay. So what happens? I mean, we looked at conservation of charge, but what happens to energy?
Oh, okay. So energy seems to be off, right? Slightly, because well, let's try it out.
Let's try it out.
Let's try it out.
Let's try it out. Okay. Let's look at it for the simple case.
Yes.
Okay. Of C1 equal to C2.
Yes.
Okay. And we have. I'll break this switch because I'm talking of the at T equal to T2 minus.
Yes.
Okay. And this is C1 charge to V, C2 charge to 0.
Yes.
Okay.
And you said C1 is equal to C2?
Yeah, sorry.
Okay.
Absolutely. So I'll just say C1 and both are equal to this.
Okay.
Okay. And after the process, right, and this process, by the way, is obviously called charge sharing.
Charge sharing.
Right, because
yes.
one capacitor is sharing its charge with the other. Okay, so this is again C. They have both come to V final, which happens to be V by 2.
Yes.
Okay, C and C.
Mm.
Okay, so what is the energy in this system?
The initial energy is of course half C times V squared.
Half C times V squared, because
yes.
the other guy is 0.
Other guy is 0.
Okay, and E final.
Yes. Here is I have half C into V by 2 the whole squared.
Half C into V by 2 the whole square.
On C1.
Yes.
And then C2 also has the same, half C into V by 2 the whole square.
Whole square, right?
Yes.
So therefore, this is half C, V squared by 4 plus V squared by 4.
So V squared by 2.
V squared by 2.
Oh, so it is 1/4 CV squared.
Yes, or it is simply half.
Half of the initial energy.
Okay, so it's funny. What we have said is the charge has actually shared.
Yes.
Charge has gone nowhere.
Yes.
Right? Absolutely nowhere.
Yes.
It's just gone from one capacitor to the another with some sharing, right? And then you find that some energy is gone.
Energy is gone.
Where did that go?
So it must have gone somewhere. Most likely, I'm guessing. So I'm looking at where else we have two capacitors.
Yeah.
We said they're ideal capacitors.
Yes.
Must have gone. If I had to take a guess, we assume that the switch is ideal.
Yeah.
But if a switch has some resistance, it will be dissipated as heat.
As heat, exactly.
The resistance.
Right? So the right way to redraw this, this picture, right? Or
yes.
After, we drew this picture, right?
Yes.
Actually, you will redraw it with some small resistance.
Yes.
Of R on.
Yes.
It's very small.
Yes.
But it doesn't matter. The beauty is it doesn't matter what the value of the resistance is.
Yes.
Whether you have a small value, large value, the energy lost is the same.
Is the same.
Right?
Yes.
Half the energy is gone.
It just depends on C and V.
Exactly.
Not on the resistance.
Not on the resistance. The resistance only determines the time.
Time it takes.
Because we are giving it enough time and seeing what happens.
Yes.
We are looking at steady state values.
Yes.
Eventually they will all come to the same voltage, whatever resistance there is.
Okay.
And energy lost will be the same.
That's right.
Right? Because essentially what we are saying is the I squared R is the instantaneous power. But
yes.
energy is power into time integrated.
That's right.
Right? So the current may be slow, but over longer time.
That's right.
Or it's fast over a shorter time.
That's right.
And therefore the energy lost is still the same.
I see.
Right?
I see. Okay.
So this is a very sort of a interesting concept that we can convey here. So half the energy is lost. So fundamentally, you do anything, you lose energy.
Yes.
There's no choice there in engineering and in science, and it's only charge that sort of remains constant in this process.
Yes.
Right?